Yeah. Okay. All right, let's get started. It's good to have you guys back for another Infosys Condensed Matter seminar series. Those of you who are here for the first time, this is a new seminar series we have started, supported by an endowment from the Infosys Foundation, and we're going to have many more talks as we go along, both international and domestic. The July month seems to be has turned out to be like the quantum month. There's a lot of talks related to quantum devices, and in that context, it's a pleasure to have Professor Takis Kontos from the Ecole Normale Superieure in Paris visiting us and giving a talk here in this seminar series. Takis did his PhD in Orsay, working on the interaction between superconductivity and ferromagnetism, and then he went on to do a postdoc in Basel, where he was looking at spin transport in carbon nanotubes, after which he got a permanent position in France, and he has been working on many topics, but one of the common features has been the use of carbon nanotubes, especially in making circuits out of them. Some of you must be familiar that one of the nice things which has happened in the recent past in the field of quantum devices is the plethora of different architectures or different kinds of devices, whether it's superconducting circuits or quantum dots or carbon nanotubes or nanowires. They all allow you to access quantum mechanics at sort of a very fundamental level, and the different architectures allow you to access various different operating regimes, each one sort of having its own benefits. And I think one of the natural things which comes out of that is that can one combine the good features of one type of architecture with another, and that sort of led to this field of hybrid quantum circuits, in which Takis has been doing a lot of work. So we welcome him today, and we look forward to his talk. So welcome, Takis.
Thank you very much, Vijay, for the introduction. It's really a pleasure to be here in this marvelous place, so I'm very glad that I could, already discuss with some of you. So this work I will present to you today has been mainly carried out by Mathieu Desjardins and Lauriane Contamin on the experimental side, and we always benefit from the theory support and inputs from Audrey Cotet. And also these are all the other students who have contributed to this work. And now a newcomer here, who you see here, François Mallet, who has just come. In fact, the team will be enlarged, also by the coming also of Zaki Lektas here. And together we will make a new team, even more hybrid than it used to be before. And on the theory side, we also benefited a lot from the theory work of Min-Chul Lee and Man-Soo Choi for the numerical renormalization group, and also from Benoît Dussault. So in the first part of my talk, so it's going to be about hybrid things today, and it will be hybrid in several different ways. So in the first part of my talk, I will just consider a situation where I try to understand what's going on for electrons in the carbon nanotube, which is in fact coupled and attached to different kinds of materials. And in fact, if you think about what it is, what happens is that every time you're trying to combine, for example, carbon nanotube, a molecule, or a nanowire, or graphene, with electrical contacts, in fact, you're making a hybrid system. So, and ultimately, if you look at this system at low temperatures, it's going to be a hybrid quantum system, right? So necessarily, if you're trying to study transport, to understand what is going on in this kind of situation, so you attach a battery to here, my working horse, which is a single-wall carbon nanotube, you will make contacts, and therefore you have a hybrid quantum system. And since, in fact, nanotubes, but the same holds for graphene or nanowires, can be combined with different kinds of materials, so they can be contacted with different kinds of materials, which can be superconducting, ferromagnetic, have different kind of electronic orders. In fact, you can imagine. You can imagine that this guy here will be able, to be connected by by different kinds of contacts here, and therefore this will alter the spectrum. For example, if you have confined electrons here, of these electrons here. And so, which means that these devices can be very interesting to answer fundamental questions in condensed matter, which is very often, let's say, what happens when I combine, let's say, this kind of feature with this other kind of feature, exactly like Vijay was mentioning. And I'm going to show you in the first part of the talk that we can push pretty far, I mean, these kind of questions and the complexity of this kind of questions. And get some interesting answers. But now there is a second, let's say now this is hybrid power 1, but this is a hybrid power 2, which can happen, is that now you can try to couple these electrons to photons, which are trapped. You see here, this is a sketch here, this green thing here, is a sketch for two mirrors of a photonic cavity. And therefore, you can try to couple these hybrid electrons to the photons, and therefore you have a hybrid square system, where now, I mean, you will try first to use the specific properties of the spectra which you have obtained in this hybrid electronic system to couple efficiently, and for example, to have some hybridized light matter states to this in this kind of geometry, where now you trap electrons, let's say in this conductor, and you also trap photons now in this big green cavity, and both, and you will in this way magnify the coupling between these two systems, and maybe make something useful, I mean, out of it. Also, another part of the coin is that if now you know how to measure very well what happens to the photons interacting with this guy, the photons will allow you to be, especially if they're trapped in that kind of cavity, to probe with a very high sensitivity the electronic properties of this system here. And I'm going to show you an example in a second. So, and in fact, for this second part of the talk, essentially, the idea, more specifically, will be to transfer all the methods which have been invented for cavity or circuit quantum electrodynamics, which have taught us how to probe and manipulate microscopic or macroscopic quantum states, to hybrid mesoscopic circuits, and in particular for us, it's going to be quantum dot circuits. And as I told you, I mean, these quantum dots which we are going to, I mean, these quantum circuits which we're going to look at can be combined to ferromagnets, superconductors, normal contacts, and essentially can also be coupled each other via the cavity mode. And this is this kind of thing which we can study in this kind of architecture. And I will show you one specific example in the second part of my talk. So in this kind of field, I mean, there may be one prominent question which one can ask: is it possible to achieve the strong coupling between the individual electronic states which are trapped in these kind of devices and the cavity photons, meaning that the coupling strength exceeds the dissipation mechanism for both in systems taken individually? And so that's the first kind of question. So but rather today I will try to answer another kind of question, which is less, which has been less studied so far, I think. Although we have studied a lot this question, is it possible in that kind of architecture, using the very high sensitivity of the photonic degree of freedom, to learn things which were not possible to learn for condensed matter physics? And my favorite condensed matter question, or like, let's say, my most prominent condensed matter situation is a situation where I cannot neglect any more electron-electron interactions, and it's a Kondo system. So, so this is going to be the second part of my talk. But let's now go back to the first part of my talk. Now, for the moment, I put the photons aside. I will only look what the electrons are doing together when I combine different ingredients. And the reason why I want to do this in this part of the talk is to find means to engineer topological superconductivity. And for me, topological superconductivity I will not get into more in the wording topological because many things can, like, let's say, can underline, I mean, this wording. But essentially, the idea is to find superconductivity in situations where the spin and the motion of the electron are coupled. For example, that kind of situation. So the question is, what happens when I have a superconductor here? So for me, it's going to be a superconducting contact. Where you have, so the pairing in a conventional superconductor is S wave, so you have a singlet state here. And when I inject Cooper pairs in a region which is a one-dimensional conductor, this is going to be the nanotube, with some spin helix, you see. So this is going to be some kind of magnetic field. For the moment, I don't specify what it is, which is inhomogeneous in space and in direction. And the question is what is going to happen in this situation for the superconducting correlations, and whether I will be able to shape essentially superconducting correlations by doing that. So this is a highly relevant situation if you want to engineer new kinds of quasi-particles which live essentially at zero energy in this system. And these are the so-called Majorana quasi-particles, which I highly sought for because they could be very interesting for doing. Some people said it would be very interesting to do some topological quantum information. But even on a more fundamental prospect, there are very interesting excitations which occur when superconductivity is induced in some spin-active materials. Because first of all, they are the O9 type particles, so which, of course, is very uncommon in nature. And moreover, they display non-abelian statistics. So if you exchange two Majoranas, the exchange of the wave function is described by unitary metrics, and it's not the scalar one, which is just a phase of pi or 2 pi. I mean, for fermions and bosons. So it's a unitary metric. So this non-abelian statistics is in fact why, I mean, this could be somehow useful for some topological protected quantum information, but I will not go into these details, into the debate of whether it would be useful, etc. So so the question is now how to shape and to engineer these systems, and essentially since let's say 2010, the usual recipe for that, if you want to make devices, of course there are people working on STM. But these are not devices, which can use a special type of spin-active materials and on a superconducting substrate. But if you want to make devices, essentially, the usual recipe is, let's say, to take a one-dimensional conductor in which you have a built-in a very strong spin-orbit interaction. You put in contact, good contact, a superconductor. You apply an external magnetic field, and essentially in this situation, you drive the system in the so-called topological regime, which is essentially summarized in this electron-hole symmetric band diagram. And essentially, it's if you have interfaces between the non-trivial, let's say non-trivial. Doesn't mean much, but the non-trivial region and a trivial region, which is sketched here. Essentially, at the interfaces, you expect to have these zero energy states, which are Majorana quasi-particles, and hopefully they are localized, and they are the O9 type particle. Okay. So, and the question I will try to address here is it possible to observe that kind of physics with no intrinsic spin-orbit coupling and with no external magnetic field? So why would it be interesting to do that? But first of all, I mean, avoiding having something which has an intrinsic spin-orbit would allow you to remove the constraint of the material. And the constraint of the material, of course, there are many, many beautiful experiments which have been carried out so far, but there are still a lot of constraints related to the material. For example, to the semiconducting nanowires, there are multi-channel character. I mean, for example, I mean, this is one example, but there are, and of course, since many people are still going on in this direction, which is, of course, I think very interesting, but removing this interesting spin orbit coupling is interesting, I mean, because it would relax the choice of the material. And do not rely on the global magnetic field would be very interesting, because this, having a large global magnetic field would, is essentially, I mean, something which is not very, like, does not, the interplay with superconductivity is not so easy. So you can also play around. But then this would be also remove a constraint. And one very important constraint which would remove the use of a global magnetic field is in 2D situations where you want to do these braiding operations, which are this exchange of two Majorana quasi-particles. This would be a very important lifting of constraint to remove the global magnetic field. And so all these things I'm going to show you now can be completely relaxed, removed by having an artificial spin orbit coupling. And now, if I do the hand shaking,